here. So, kind of where are we at? So we've got that quiz that's due by the time we start class on Thursday. So it shouldn't be any of the material like we're covering today or even last Thursday. Anything before last Thursday should be fair game. That set of practice questions should look pretty similar, kind of the type of questions you'll see on that quiz. You know, I try to reiterate this. And I put it, oh, let's see. Forgot the view's a little bit different. But remember on those quizzes, you know, once you kind of start these, so I didn't put this in the description for quiz 3, so I failed to do that. I apologize. So there's a kind of running clock once you start it, right? So once you start, you'll have 60 minutes to finish it. So I forgot to put that in the description for that quiz. I'll get that updated after class, but there's a reminder, once you start those, you have 60 minutes to complete them, okay? I failed to put it in that one. It's kind of the same, so it's in the syllabus, kind of always consistent. The other thing we currently have out there is that third problem set. So I would try to start getting that out of the way. I think I have the due date set to be what? The 4th is next Tuesday. So by the time we start class, and that's because what's next Thursday? Yeah, so we'll have that first exam, right? So I would try to get that problem set due well before that due date, right? I've also put up, you know, those quizzes and then those sample questions are good things to look at. But if you want kind of something that's going to look, I've gotten some questions. Where is it? Midterm exam materials. So first of all, as we kind of start thinking about doing some review, which we'll probably do a lot of review in class Thursday. So I'll be doing things in Stata, but I'm also going to show you, you know, on the exam what it's going to look like. I'm not going to have you use your computer. You're not going to be doing any coding or anything in Stata, right? So what you might have to do, like similar to some of the questions I put in the problem set, is maybe I give you some Stata output and you have to answer questions about it. Okay? So here's the formula sheet. It should have any formula that you would need, right, to answer any question on the exam. You'll have this on the exam, okay? So I'll kind of start referencing this as we start to do some review, but you'll have that, you know, it's up there. You can see what it looks like on Canvas. You'll have that going into the exam. I also put up this set of practice problems. So notice, I'm giving you like Stata output here and then asking you some questions about it. I'm giving you some regression output. I'm asking you some open-ended questions, maybe multiple choice. So the structure of the exam is going to be a little different. I'm going to kind of put all the multiple choice questions together and then kind of have a short answer portion. But this is going to give you kind of all different types of problems you could kind of think about seeing, right? A mix of short answer and multiple choice on these various concepts, right? So this is going to be a really good study tool for the exam. So I would, you know, feel very comfortable with that practice exam. You know, I've got the answers posted up there as well. So a good thing might be, you guys are far enough into the game. Maybe I don't need to kind of go over this, but I would sit down and try to answer all those questions without looking at the answer key first, right? Then I would go through the answer key, see which ones, which ones did I not know how to do, which ones was I really far off from what the correct answer was. Those would be good ones, which might, you know, those would be questions which would be good to ask me questions on, either during office hours, either tomorrow or next week, or in class. Kind of Tuesday, we'll be doing only review next week. Like I said, Thursday, I'm guessing we'll mostly be doing review. Now, it might be a little bit more, less on those practice exam questions and a little bit more targeted. I might show you some different examples that might be helpful to kind of work through. But really, from here on out, after today's class, it's no new material in terms of there's no new topics, okay? Any questions for me? I think that should cover it before we kind of jump in. The last little bit of new material that we have today, we'll revisit some things we've already talked about, and then we'll also kind of look at one new thing, okay? So I've got these week 7 slides, and then also that week 7 multiple linear regressions do file. So we're using both of these, okay? So might be asking you guys a lot more questions, a little bit less of me kind of telling. So let's say I had something like this, right? So I gave you some regression output. So this is where I might not write out. Now on the exam, you'll kind of see probably from that practice exam, I would likely on the exam also give you what the actual regression equation is. But here using this code, what's my Y variable? Wage, right? It's the first variable there. So I'm going to write something down and then we'll kind of switch over to it. What are the 3 variables that I'm looking at? Independent variables of IQ, age, and experience. Right? So what I'm thinking about here is I always have an intercept when I'm running a regression. I then have IQ as that first variable. Age was the second. Now I'm already forgetting. Was the other one experience? Yeah. Okay. So this is going to be our regression equation. Now I gave you the output. So what does that output include? The estimates for every single one of these slope coefficients. So if we look at that, I think the constant was like, I'm going to round pretty egregiously here, but 8.42, 23.17, and negative 1.44. So if I want to know the predicted wage of someone who's has 105 IQ, 10 years of experience, and is 45 years old, what do I need to do here? So once I have these coefficients, that allows me to come up with predicted values for my dependent variable. So what do I need to do? Just take those values of 105, 10, and 45 and yeah, if we don't know this, this is a problem, right? You should be able to make these very easy predictions where I'm giving you the person's IQ, I'm giving you, I forgot what it was, their age, and I'm giving you their years of experience. It's just a linear equation. That's all linear regression is. We're using data to come up with a linear equation to make predictions about our Y variable, okay? So that should hopefully be an easy question on the exam if I give you something like that. I can almost guarantee you I'll give you something like that. I might even give you something like that from a simple linear regression with only one variable. Should be even easier. Right? Any questions about this? Okay. So, you know, how would I kind of do this, right? How can I make predictions or find errors in data? So just to kind of review, this might be helpful for the problem set or kind of problem sets in the future. So I'm going to look at this. I'm going to use one of these kind of free data sets. I'm just going to clear this out, kind of call this BQ smoke. That should open up one of these free data sets that exists kind of with smoking data. Right? So this is, I'm running a regression. I'm thinking about, here's the number of cigarettes someone uses. I think this was per day or per month, their education, cigarette price, a race identifier, their age and income. Okay. So I think we started to look at this a little bit last class. I can't remember if I used this data set or not, but if I run a regression, instead of just always doing this by hand, which that's what we're going to need to be able to do for the exam, right? So it's a little bit harder to think about when we're thinking about like the coding way to do it in Stata, which is, let's say I want to make the predicted number of cigarettes used by someone with 12 years of education, $5 is the average cigarette price, et cetera, right? So if I'm looking at this regression, right, I've got my different coefficients. All I really want to do is take the intercept, add to that the coefficient on education times the person's education, which was 12 years. Then add to that the coefficient on cigarette price times the cigarette price, which was $5. We said one way I can do that in Stata, anytime I run a regression, it temporarily stores all of those coefficients behind the scenes. How do I use those coefficients instead of having to type out the answers out to the 7th decimal? This underscore B, and then in square brackets, I put whatever variable I want to use the coefficient of. So education, it was just EDUC was the name of the variable. So this is the coefficient on education multiplied by, well, what was my hypothetical person? They had 12 years of education. Add to that the coefficient on that cigarette price times what was the hypothetical cigarette price? $5, et cetera. So I did that for every single variable here. Now, the one that's a little tricky is that intercept, because Stata always calls it the constant. And the way that it, for whatever reason, it throws an underscore in front of it. I don't know why it does that. I think there's probably some coding things on the back end where it uses CONS for something else, but there's always going to be an underscore in front of that. So when we're making these predictions, we don't want to forget to add in that constant. Okay, that can give us wildly different predictions. Okay, so if I use this method and kind of use this display command, that'll work. Right? Now I could also generate a new variable, which was just equal to this, right? I then can kind of take a look at, okay, what was that prediction? Well, it's not really the most efficient way to do that because I now have a new variable in my data set. It's all the same value. That's probably don't want to do that in practice. But for us at this point, by all means, that's fine. right? If I'm just asking you to find the value, you could also create a new variable to find that value as well. Okay. Any other questions on that before we keep moving? So I think we did this a little bit last class. Now, another thing we can do is use the predict command. Now, the predict command, the only problem is it'll predict our Y value, but it's going to do so for every single observation. So we can't really do it for like this hypothetical person, right? But we might want to do that, right? Because what is one of the assumptions that we have in our regression is that the expected value of the errors was equal to. So remember, when we're drawing this line of best fit, we have a scatter plot. Where are we drawing it? We're trying to kind of draw it like through that's like scatter plot so that there's equal observations, like equidistant observations above and below it, or essentially our error, the expected value would be 0. We want our predictions to be good, right? So we want the error, the difference between the actual Y and the predicted Y to be 0. So we said one way we could look at this is use this predict command, but instead of predicting the Y value, which is I think how I showed you to do it a while back, you can predict the error term by putting this comma residuals in there, right? So if we go ahead and do that, and then summarize that error term, hopefully we get an error term that has a mean that's really close to 0. Once again, we're looking at stata output. Remember, these e's to the negative or e's to the positive, that means move the decimal that many places to the left or right. So this is what, 0.00000002. This is basically an expected value of 0, right? We have an error term with the expected value of 0. That's great. It's one of our assumptions that we had, so looks like that's upheld. Okay. What else do I want to do here? So I'm going to jump ahead a little bit. What did I have? Oh, well, see where I'm at in the slides. I'll try to coincide with the slides, not jump the gun too much. Okay. So let's think about a different example, and then we'll come back to this cigarette data. So let's say, we can look at that output. So before, which of these variables can we say have a statistically significant effect on wages? What would I look at? Two things. One thing, I could look at the p-value. So which of these look like they're statistically significant at any level? IQ and age. Experience, not so much. Now, just to kind of rehash some things we've talked about, why might that p-value on experience be really high? Something we talked about last Thursday. What might the age and experience variable have?
No, is it like collinear?
Yeah, right. So bias, that's thinking about omitted variable bias, where that's going to impact our coefficients. We said one thing that won't impact our coefficients, but it will impact our statistical significance, was if two variables are collinear or imperfectly collinear. So that would probably be age and experience here. Just kind of revisiting some of these things along the way. So I've got my statistical significance, but I mean, I don't know, is being 1 year older, is having $23 more actually that large of an effect? Now, I think these were like hourly wages, so maybe it is, right? I can't remember off the top of my head, to be honest, what wage was, so what would I want to do? Well, what would tell me if that effect was large, what we would say economically? So statistically, very significant. The economic significance is it a large effect? Is the magnitude large? So what's one thing I could do? If I think about it increases my hourly wage by $23, well, that's a pretty small effect if the hourly wage is, I don't know, if this was like monthly wages, if wages is like in the thousands, that's a very small effect. But if this is an hourly wage, the effect of $23 an hour would be really large. What am I doing there? I'm comparing it to kind of what the average of that Y variable is, right? Sorry. Yeah, the average of that Y variable, dependent variable. Yeah.
Like when our age increases, your wage is expected to go up, but you're experience.
So it'd be hard to disentangle the effects, right? Because anytime I'm a year older, what has to be true about if I'm a year older, inherently, what's going to also happen to my experience if I have a job? Yeah, so maybe I do still have some bias that's built in, where there's these things that are like correlated with age and experience that are causing these coefficients to be, this is a pretty naive regression. I only have 3 variables. So probably don't want to put a whole lot of stock in these, because I might have some important omitted variables that are affecting the size of the coefficient, or in this case, maybe even the sign. right? If the bias is large enough. In fact, what can I explain? About 88%, right? If I'm looking at the R squared there. So there's probably some important omitted variables. Right? That's not being caused by the collinearity though.
Okay.
Yeah, the collinearity is only going to impact our statistical significance. So think of another example. So let's say I find the effect, I want to run this prediction. What's the effect of the unemployment rate on GDP? I run this regression. I see, okay, GDP, every time unemployment goes up by 1%, GDP falls by $10 million here. Well, that might seem like a really large effect, right? The 1 unit change in unemployment causes my Y variable to go down by 10,000. But well, how do we measure GDPs? Are they even in the millions? No, right? I mean, we're talking, trillion. I mean, we're talking insanely high values. So 10 million might not be a very large economic effect, right? So what might we want to do? A lot of times what we'll do is we'll scale that effect to see, does it have economic significance, right? What percent of the dependent variables mean is our coefficient, right? So what, if I had a mean of say 10 billion here, right? Well, what would the effect of 10 million be? If I take 10 million over 10 billion, I've got what? This is only going to be like a 0.1% change. That's a pretty small economic change, right? Economic significance would be relatively small there. So we don't want to get too hung up on statistical significance. We can find what's always going to make sure we can find statistical significance. One thing we said, if we go out and get more. So this is good. We're kind of rehashing some things. If I'm thinking about my test statistic, we said that's here, right? So in my standard error equation, kind of think about, this is what? We'll take our predicted average squared over n minus 1. So if n is going up, what's going to happen to my standard error? My standard error goes down, what's happening to my test statistic? If my test statistic is going up, what's happening to my p-value? Remember, how do we find a p-value? It's the area or the probability of seeing that test statistic or something more extreme. So if I see a larger test statistic, what's happening to my p-value? It's going down, which means is it more or less likely I reject the null? We only reject the null if my p-value is less than that. Alpha is not changing. Those are those same 3 benchmarks we always use. So it's going to be more likely. So anytime I increase my sample size, I can always get closer and closer to finding statistical significance. Now, the economic significance, that's not going to be impacted by my sample size, right? That's telling me what the size of the effect was relative to the average Y variable. So we could think about doing something like this with our cigarette price data. Okay? So here, thinking about, we just divide the coefficient by the mean of that dependent variable. And then if we want it in terms of a percentage, we would multiply by 100, right? So let's take a look at what this would look like in Stata here. So let's say, scrolling around too much here. There we go. So I'm going to run this regression where I try to predict cigarette use with these same variables that we had before. Now I'm going to look and see, okay, education looks like it has, at what levels would it have be statistically significant? So what would I look at? The p-value. Is it less than 0.1? 0.027. Is that less than 0.1? Yes. So I would say it's statistically significant at the 10% significance level, or what confidence level? 90%. Is it statistically significant at the 95% confidence level? Well, what would alpha be there? So the 95% confidence interval would be 5% significance. Alpha is our significance level in decimal form, so 0.05, less than 0.05 as well. So we've got statistical significance at the 90 and 95% level. What about the 99% confidence level? Well, there, what would my significance level be? 1%. Alpha is the decimal form of that, 0.01, not quite less than that. So we only found statistical significance at 90 and 95% levels. Also, to kind of just connect the dots here, this might be a question I ask, because I've written the exam. So can I reject the null? So what is the null hypothesis I start out with for all of my coefficients? that the coefficient is equal to 0, no effect, right? If I can reject that, I'm saying I found evidence there is an effect. So at the 95% confidence level, I was rejecting that the true value is 0. So my 95% confidence interval, what value do I know for sure won't be in that interval? If I'm rejecting 0, is 0 going to be in that interval? No. So I can use the p-value to make my rejection decision, but even if I like put a white box over this p-value column, and let's say I put even a white box over the test statistic, because even if you didn't have the p-value, what else could you do? Compare that test statistic to what? Our critical values, which we kind of said, our benchmark, we're going to use a standard normal just to approximate. We're not going to worry about using those student t-tables, get the exact value. Our data sets are usually large enough to where we can use the standard normal. So I think at the very top of the exam, I'll give them to you and remind you of them, but they're 1.65, 1.96, 2.58. So here, I could compare that test statistic. It would be greater than in absolute value than 1.65 and 1.96. So we make the same rejection decisions we did before, but not greater than 2.58. Okay? Or in absolute value. Sorry, I know I forgot it's negative here. But when we can reject it, even if I left out both of these columns, I couldn't necessarily ask you about the 99 or 90% level, but if I gave you the confidence interval, you know that you can reject any value at the 95% level that's not in that range. What's one of the values not in that range? Well, these are only negative values. 0 is not in my confidence interval. Okay? So anytime we can reject that null hypothesis using our p-value, we shouldn't see 0 in our confidence interval, right? Because we're rejecting that as one of the possible true values. Okay? A little bit of an aside, but once again, I'm trying to start to incorporate some exam review here, kind of going back and reviewing some things. So that effective education is negative 0.37, right? So I don't know, the cigarette use, once again, I can't remember if this is weekly or monthly, but whatever it is, it's going down by 0.37 cigarettes for every year of education. Is that a large effect? Well, what's the average cigarette use here? Well, once again, if I can't remember what the variable is, let's try to get an idea about it, right? So if I summarize that cigarette variable, okay, I don't know, I'm going to guess this is like, well, maybe it's daily. Hopefully it's weekly. But if it's daily, right, this would be that the average cigarette use in this data set is what? 8.6 cigarettes a day, right? So would the effect of like 0.4 of a cigarette be relatively large? Well, I don't know. I mean, if I look at that kind of ratio, it's about a 4.3% increase. That's not nothing, right? That's not crazy high, right? But it's also not, you know, really, really small, like the GDP example, we had like a 0.1% increase. So we can also think about economic significance along with the statistical significance as well. Even if we find strong statistical significance, if the effect is relatively small economically, we might not care as much about that variable either. Yeah. A little bit more of a philosophical kind of question, maybe not as many questions thinking about on the exam there, but I want to kind of round out our discussion about what we're doing with regression here. Okay. So the next thing I think I have in the slides, and we'll kind of stay here and state it to represent it. We've already talked about this a little bit, but I might give you some questions where you have to scale a variable. So notice here, if I'm thinking about that income variable, okay, this is an older data set. It was younger individuals, so the mean is relatively small, right? $19,000 in income. Maybe this was like, you know, a lot of students in this data set. I forget exactly where they scraped all this data from. So my mean is, you know, about 20,000 here, okay? So what's going to be the unit change in income? It's going to be having one additional dollar. What is the size of that coefficient going to be? The effect of having one more dollar on the number of cigarettes you smoke is going to be really, really small. The units are small. So what might make sense sometimes is, well, let's think about a different unit, right? So I'm going to create this new income variable where I divide income by 1,000. So now every unit increase, so think about it this way, income was 20,000. Now, what would that be if I divide it by 1,000? 20,000 over 1,000 is, I'm going to say, we can't do this. I might write some letters about not letting you guys get an IU degree. I don't think we want, you know, so I'm joking. So we have 20, right? So now what's a unit increase? Going from 19 to 20 would actually be $1,000. So what's the size? What's going to happen if I run the exact same regression, same variables, all the same control variables, but I use my scaled version of income? If I scale it, depends on how you want to think about it, but scale it down so it's like a smaller value, so every unit represents a larger number of dollar increase, what should be true about the size of that coefficient? Well, now it's not a $1 increase impact on cigarette use, it's a $1,000 increase, so the effect should be larger, right? So if I run this regression and I remember to create my new variable, there we go. Now, when I'm looking at that income variable, notice what was the coefficient before? 0.0001. Not surprising, that was a $1 change. A $1,000 increase, it would go up by 0.117. Well, now notice, yes, it got larger, but what did all that do to my coefficient? These are the same numbers. All it's doing is giving me the same coefficient, but just moving that decimal, making it a little bit more manageable to kind of make these interpretations. Okay? So it's going to change the size of my coefficient when I scale a variable. But if I'm just changing the units, what should happen to the statistical significance? Think about it this way. When I'm calculating test statistics, and I've got like my coefficient, my standard error, what are the units for both of those? Well, they used to be in dollars, now they're in thousands. But if they're the same, the units will always cancel. So my test statistic will always be the same. So my p-value will always be the same. So the statistical significance, if we scale variables, linearly scale them, we don't do some like goofy, like, I don't know, instead of just dividing or multiplying, we do like multiply by something squared to something else to the q, right? Some crazy transformation. We're just kind of doing this nice multiplication or division, just scaling the units. We're going to end up with the exact same p-value. So 0.036, 0.036, right? So it won't change our statistical significance. It just changes our interpretation to make it a little bit more usable. So we can scale variables whenever we want to, right? It'll change the coefficient because that's changed the units. But in terms of our statistical significance, we shouldn't have any impact. Any questions on that before we keep moving? So if I'm using the same variable and all I'm doing is scaling it, what do you think also happens to my R squared? So if I'm just scaling it, have I provided any new or gotten rid of any old information? Still the same underlying variation in that variable. It's just we're scaling the units. So notice what's happened in my R squared, 0.1298, 0.1928. No, 0.1298, sorry. All right, hasn't changed my R squared at all. So we can scale variable without really, worry about impacting other statistics. The only thing that's going to impact is that coefficient on the variable we scale. Okay. We've talked about standardizing. I don't want to waste today's class. We might revisit this on Thursday. So the other thing that I want to make sure we get today. So we talked about scaling, economic significance and scaling. We can do these things where we standardize it. Why do we want to standardize it? If I standardize a variable, we said the interpretation of my coefficient is now a 1. So what's the unit of a standardized variable? If it increases by 1 standard deviation, right? So that kind of incorporates like, oh, there might be less variation in this variable than others. And so it's kind of giving us like a better idea of like, we're not having to worry about the units, right? We know it's like a standard deviation increase. I won't go past that. I'll kind of gloss over that for today. We might revisit this on Thursday. So something else that we also talked about was the adjusted R squared. So I just want to kind of reiterate this. So what are some things that we're doing? We're adding in variables or we're getting larger data sets. There's 2 things that can really impact our adjusted R squared, right? And I think, the notation I'll use is often this. I'm just writing adjusted to make it a little bit easier to think about this. So usually our R squared measure, regular R squared, is the sum of the squares that our model explains over the total sum of the squares. So all this meant was the variation our model explains divided by the total variation. It's kind of that ratio. So the adjusted R squared, another way of writing this, if this is the proportion I can explain, that's the same as 1 minus the proportion that I can't explain. So that was what we call our residual sum of squares. This is the variation that existed that we couldn't explain. So all the adjusted R squared does is take this proportion that we can't explain and scale it by this factor. Okay. Now we said, what's going to be true about this fraction? It's always going to be what? I can say it's less than or greater than a specific value. So put some numbers to it if it helps. If this was 10, this was 1, 10 minus 1 is 9, 10 minus 2 is, I'm always going to be subtracting something else. So the denominator is always going to be smaller. So this fraction will always be something a little bit larger than 1. So what's going to be true about my adjusted R squared relative to my R squared? It's always going to be, so if this is greater than 1, I'm going to be subtracting a larger value. So if I subtract a larger value, my adjusted R squared will always be, sorry, I'm writing this backwards now. My adjusted R squared will always be less than my R squared, right? That's why we're adjusting it. We're kind of saying, okay, look, the reason why we're going to adjust this is because I know two things are always true. If I increase my sample size, artificially, what can I always do? Even if I find the same coefficients, the same exact R squared, but I did it using a larger sample size, well, what is this sample size going to do to my adjusted R squared? Okay. Well, I found the same. So let's say I had one data set of 100. I found an R squared of 0.2. I have another data set of 1,000. I find the same R squared of 0.2. You can kind of think about it this way. Each data point was like less valuable, right? I didn't really need as much of that data in the second one to find the same statistic. So we want to account for the fact that if we find the same R squared, but using larger data sets, we want to kind of penalize ourselves for that, right? Because we can always kind of change these. We already talked about the test statistic, right? We can always change the coefficient's statistical significance by just getting a larger sample size. So if I were to increase my sample size, it's a little bit trickier to think here, but if we use really small values, if n was 2, well, if n is 3 and k was 1, this would be what? 3 minus 1, 3 minus 2, so this would be what? 2 over 1, so this factor would be 2. What if I go to 4? 4 minus 1 is 3, 4 minus 2 is 2. I'm now down to 1/2. So as I'm kind of increasing my sample size, what's happening to this scaling factor? It's going down. If it's smaller, I'm subtracting a smaller amount. So my adjusted R squared is going to do what? If I'm subtracting a smaller amount, the adjusted R squared will go up. Right? So the adjusted R squared is penalized more when we have really small sample sizes. The second thing we think about changing is if I just start throwing in more independent variables. That's what K represented. So I just start throwing the kitchen sink at that cigarette price prediction. I just put all this stuff in that maybe doesn't even matter. I don't know, the temperature outside, all this other stuff, right? Well, what's that going to do to this scaling factor? If I increase K, so I'm subtracting a larger amount here, the denominator is actually going to get, whoops, never mind, sorry. I'm subtracting a larger value, so my denominator is going to go down. My denominator goes down, what happens to my fraction? Goes up. If I'm subtracting a larger amount, what's happening to my adjusted R squared? Yeah, if I'm subtracting a larger amount, it's actually going to go down. Well, I forgot to put the what's going down. Sorry, adjusted R squared is going down. So increasing my number of independent variables I put in my regression, that's going to drive that adjusted R squared down. We want to kind of penalize ourselves for just throwing in more variables there. Okay? Because I can always increase my R squared if I just throw in variables, and even if they don't really have that much really relevance on my dependent variable, they'll still increase it a little bit. Okay? So these are going to be the kind of two factors that can influence our adjusted R squared. Any questions on this? Once again, I know we talked about this before, but just kind of revisiting it a little bit. All right, so kind of come down here. I think I had some examples. Oh, I can kind of prove this to you a little bit. So let's say I run this regression. Well, here's the first one. What am I doing from regression 1 to regression 2? I'm including what? You can't see it because I didn't hit it hard enough. There we go. From my first to my second regression, what am I doing? I'm including more independent variables. So yes, that in and of itself might decrease my adjusted R squared, but this is where we have to be a little careful, because what if those are really important variables? What if they explain a lot about cigarette use? Well, even though the adjusted R squared is going to go down a little bit because I used more variables, if they explain a lot of the variation, it might be kind of overcompensated for that. So I can't always say what's going to happen to my adjusted R squared, but I know the impact of K is only on my adjusted R squared. So even if my R squared goes up, by adding in these variables, it's going to impact not my R squared, but it will impact my adjusted R squared. So what's going to happen to the gap in between the two? That I can for sure say is going to get larger. I can't say that my adjusted R squared for sure will go down in total because the R squared itself might go up, right? My residual sum of squares might be going down, right? This part of my adjusted R squared equation might be going down. However, K doesn't impact R squared at all. It will still impact the adjusted, so it might cause that gap to widen. So we're going to look and see if this is the case here. So I'm going to run both of these regressions. We've got one. We start out with R squared is 0.019, adjusted R squared is 0.015. So what? 0.005 is about the gap in between the two. Well, notice these two variables must not have a lot of predictive power because what happened to my R squared? It actually stayed basically the same. So I tried to find variables where this was true. It's not exactly the same. If you go out to enough decimals, it did go up a little bit because we included more variables. But what happened to the adjusted R squared? What happened to the gap in between my R squared and adjusted R squared? Before it was only 0.005. Now it's what? About 0.00, a little bit more than 7. So it did grow a little bit, right? That including more independent variables impacts my adjusted R squared, doesn't kind of factor in to that R squared calculation. Okay. Any questions on this idea? So now using this one, let's say I take a random sample and I run it with only 100 observations. So assuming that it's random, the R squared actually shouldn't change much at all. Now it might change because it is a different sample, so it might change a little bit. But if I'm randomly sampling from a larger sample, my R squared value shouldn't change much. But having a larger sample size, we said did what? It was actually going to cause my adjusted R squared to be a little bit higher. So think about it this way. If I get more data, I don't need to make an adjustment as much. So the gap in between my R squared and adjusted R squared will get smaller and smaller. Here I'm going the opposite direction. I'm getting a smaller data set. So what's going to happen? The gap between my R squared and adjusted R squared is going to get larger, right? So if I go ahead and run this, sure enough, I say, okay, my R squared before was 0.019, adjusted was 0.011. Okay, well, the R squared did change here. It was a different sample. But here what we're really focusing on is what was the gap in between these two? Instead of 0.005, now it's like what, almost 0.06. And we get this really weird thing where if I have a small sample size, notice what happens to my adjusted R squared? It becomes negative. It doesn't even really mean any. I mean, we can't even really interpret this. What this is essentially telling us, if we ever got an adjusted R squared that's less than 0, it's saying based off the data you have and the number of independent variables you use, there's not enough variation in the data for us to really be running this regression. We really shouldn't be, right? Because when we made this adjustment, based off the sample size and the number of independent variables, we're getting an adjusted R squared, meaning the adjusted proportion you can explain is less than 0. All right, that means these probably aren't very good regressions. Now, 100 observations, that's not very large of a sample size. So we can end up with small sample sizes this weird scenario where we get an adjusted R-squared that's negative. Right? But here I'm kind of using this to kind of show you that the size, kind of that difference in between R-squared and adjusted R-squared will grow. Okay. All right. So I'll have to go back and change the quiz. Well, 1, 2, 3, 4, 5, 6. All right, I got a different idea. So we'll keep going here. The last thing that I want to kind of get through is doing something called joint hypothesis testing. So we won't, I'll show you some nasty equations that I'm not going to make you use. We'll kind of get at the idea that it's going to be pretty easy, actually. These questions shouldn't be bad in the exam. So what if instead I think about that example where I just added 2 variables into the regression, and I want to compare that first model without them to the second model with them. I want to say, did adding these 2 additional variables actually provide an additional explanation of my dependent y variable, simultaneously adding them, not one at a time. If I want to know one at a time, what do? I just look at the statistical significance on each coefficient. I want to know if adding them at the same time had joint significance. Well, the problem is we didn't go too deep about type 1 errors, but this was the idea that when we were making this rejection decision, our p-value, we'll make rejection decisions sometimes when we shouldn't be. And what ends up being true if I want to make this for both, well, let's say I wanted to do this at the 5% significance level. That really is telling me I'll be making errors with my rejection decision based off my sample data 5% of the time. Well, if I'm doing that for 2 variables, it's actually 0.05 times 0.05, which means I'm making errors less than 0.025 would be multiple. So it doesn't quite work out to be the same, right? So that's not, I went too fast. That's not our type 1 error we wanted. So we got a little bit of work to do, right? So I'm going to throw this out at you, and then we'll kind of say, okay, what do we really need to take away from this? Okay? So if you want to ever do joint significance testing for 2 variables, we're going to actually have to use this F distribution. I'm not going to make you use the F table. I think I threw it up there on Canvas. You can take a look at it. But ultimately, it works the same way as our other rejection decisions, other than this is actually only a one-tailed test. Because when I add in variables, what has to happen to my R-squared? It's going to go up. Now notice there's some weird notation here, but this sum of the squared residuals, right? This is going to be kind of thinking about, actually, I want my unrestricted model. This shouldn't be, I think I flipped these. I did, definitely did. My restricted, sum of the square residuals. I should always be explaining. Nope, I had it right. I'm overthinking this. I should just trust myself when I do these things before class. So what this is really telling us. So SS, this like residual sum of squares, that was how much we couldn't explain. So here we're going to call the restricted model the one where we didn't include these 2 additional variables. So the proportion of variation that I can't explain will always be higher from that restricted model. My unrestricted model is when I include these additional variables. So the amount of variation I can't explain when I add more variables in should always be a little bit lower. So what's this value always going to be? Positive. We're always going to have a right-tailed test. So instead of 2-tailed tests, we'll have a right-tailed test here. Okay. So if we run these regressions, we can actually grab these values, the residual sum of squares, from both the restricted and the unrestricted model. Q is going to be the number of restrictions. So in the easy example I just set up, it was only adding 2 variables. So Q there would be 2. If I wanted to jointly test 4 variables, my Q would be 4. K, right, in the denominator, that's just going to be the total number of independent variables that we had in that final unrestricted model. Okay, so I'll kind of walk through an actual example and state it here, kind of say how we would kind of come up with that F statistic. I'm probably going to be a little bit more concerned with, though, giving you the output that runs this test for us in Stata, and just knowing if you can make that rejection decision looking at the p-value and what that's really telling. So if I come up with this F statistic, right, and we've got degrees of freedom for the F table, I'm not going to make you actually physically use it because Stata is going to spit out at us the p-value we would find if we used the F table. We're gonna cheat. Okay? So if I find a small p-value that's less than alpha, I can reject, right? So if I'm more likely to reject, what am I rejecting? I'm going to start out just like everything, assuming that what I added had no effect. So if I can reject that, what am I really saying? This unrestricted model where I included more variables, they had a simultaneous effect where the amount of variation I can explain actually went up. So if I can reject the null with this test, right, that we're going to see in Stata, that's saying that the variables I added in explain a statistically significant amount more of the variation in our y variable.
Would this just be like the same as like taking your unrestricted models, R squared and subtracting?
So, right, you could
It just does it.
you could rewrite this equation, right? Because if I have the residual sum of squares, I could rewrite that as a function of the explained sum of squares and the total sum of squares. You would just have more statistics kind of floating around here. But you could definitely write this in terms of your R squared as well. Is that what you're asking?
I'm asking that is this the difference between the R squares that? Or is this something different?
If it's easier for you to think about it that way, yes.
Okay.
So
So instead
I want to
of
be careful with my words. Yes, you can think of it that way. It's this F statistic essentially measures how much more of the variation you can explain. So another way of thinking about that is, did my R squared from that unrestricted model actually increase? Now, it's not quite just looking at, did it increase? Because what are we doing? We're scaling it. We can always increase it if we add 100 instead of 2 variables. So we're looking at that difference and scaling it by the number of variables we use. We're also scaling it by, we know that kind of the sample size is going to matter as well.
would it end up being the same number? Or
If I use the R squared,
like would it be the same number? That's kind of what I'm saying. Is this like did you also just say it's R squared unrestricted minus R squared restricted? Or is this kind of have like
I kind of forget. I'd have to do the math myself, but I can kind of show you, I think, what you're asking. So we had, so I'll just even do this part. What's my R squared? That's my explained sum of squares over total, or we said 1 minus the sum of the squared residuals over the total. So what? I can rewrite this as, like, move things over. I'd have what, SSR over TSS is equal to 1 minus my R squared, which is equal to 1 minus my explained sum of squares over total. This would be total over total. So I'd have what? Total minus explained is equal to SSR over total, multiply. I've got what? TSS squared is, so it won't quite be my R. You see what I'm like? You'd have to work through the algebra exactly what it would be, but it is some function. Like R squared is floating around behind the scenes there, because I can always rewrite what I can explain as a function of what I can explain. Does that make sense?
Yeah.
This is just kind of the formula I'm going to give you on the exam.
Yeah.
It'll be a little bit more, but if it helps to think about it, there's 2 ways to think about the statistic. It's measuring, am I explaining more of the variation, or by using the residual sum of squares, is the amount that I can't explain going down? Is that,
Yeah.
So yeah, you can think of it either way. Let me see if there's anything else I want to say here. I think I just want to show you some examples here in Stata. So here's, I think, your question answered. I guess here's the math, right? You can kind of think about it as the difference here. It just gets kind of weird here because in your denominator, you don't have the difference between the restricted and unrestricted. So that's usually why we think about it as the proportion that we can explain, but you can rewrite it using the R squared values as well. Let me show you an example of this. Let's see, do I have, yeah, so I had here. So let me run this. Oh, do I not have it? So NC, oh, because I have the wrong global. So let's open this up. NC, Indiana, don't save. Let me get this for next class to make sure I've got the right global. I forgot to update this. So my new folder is right there. So let's say I just created this thing where I took a small sample size. Actually, did I already do this for the one I uploaded for you guys? No. So this is 10,000 observations. I just want to kind of, oh, well, never mind. We'll use this for next class. So let's say I had this regression where I want to try to predict math scores using the grade the individual's in and whether or not they were identified as a male student. Not that crazy. Right? So I run this regression, I can kind of see I've got a really low R squared here, right? So my R squared is very, very low. And I think, okay, well, what if I included whether or not the student was identified as exceptional or learning disabled? Well, those variables, if I'm trying to predict math scores, what do you think is probably going to happen to my R squared? If I'm now adding in information of whether the student, not just the grade they're in and whether or not they're male, but whether or not they're identified as exceptional, what do you think is going to happen to the R squared when I'm trying to explain math scores? It's going to go way up, right? So we can now run this regression where I included those two and notice, okay, yeah, I went from like 0.001 to my R squared is at least now over 10%, right? It's above 0.1. So when we include these additional variables ahead of time, we probably could have guessed, like they're going to allow us to kind of explain more of the variation. Now, can we explain a statistically significant amount more of the variation? Okay. Well, I can use this test command, right? And so this is maybe what I would do on the exam. Instead of making you calculate the F statistic, go through the F table, look up the p-value, I'll give you stata output that takes these two regressions and tests for the joint significance of these two, right? So what that output looks like is something like this. Well, why is this F statistic so large? Well, my R squared went from what? 0.001 to 0.1. That was a huge increase. Not only that, I had a really large sample size. So like everything, really large sample sizes makes it easier to find statistical significance. Right? So here I can very easily reject the null that these have no joint significance. Or I found strong evidence that they do, which would be evidence that they should be included in my model. If I worked the other direction, so let's say I took these two regressions, and instead, I started out with my restricted model. I was only including these two variables. So I start out just using the exceptional and learning disabled. I'm getting about 0.1075. Now, if I add in grade and whether or not that student is male, what's happened to my R squared? Well, it's went up, right? I went from 0.1075 to 0.1085, but it barely went up, right? And so can I say that adding those variables was statistically significant? Am I explaining a statistically significant amount more of the variation in my math scores? Well, what I can do here, use the IM test. What variables am I now testing? Well, now I added in, if I can type, my gosh, why is it not? There we go. Now I'm testing whether or not adding grade and male in increased the proportion of variation I could explain. So now if I run this, why isn't it like this? Because it's not IM test. I'm mixing this up with something else. It's just test, right? So adding in that variable of grade and male, does that allow me to explain more of the variation in math scores? Not at any conventional statistically significant level. My p-value is 0.67 here. So I failed to reject at any level. So here you can kind of run the test both ways, right? I can do a joint significance test for the grade and male variable. There I found that doesn't really allow me to explain that much more of the variation. But if I kind of test the joint significance of these exceptional and learning disabled variables, it looks like they allow me to explain a lot more of the variation, or at least I can explain more of the variation at a high statistically significance level or significant level. Do you have a question?
Yeah, if you look at that test and we see that like, we interpret it as statistically significant.
Mhm.
If the variables used are totally different, so that like
So you're thinking about if I'm doing a joint significance test for imperfectly multicollinear variables, it's going to screw with my joint significance test as well. So just like it impacted the statistical significance of one of my variables, it should impact both as well. Or sorry, it should impact the joint significance test if I'm running it for both of them as well. Yep. Because think about it, like when I did my first example where I said like the type 1 error was 0.05 times 0.05, we already know that that type 1 error is going to be wrong because of the imperfect multicollinearity. So this doesn't actually account for that imperfect multicollinearity. Yep. I wouldn't push you that far, but that's a good question. Yeah. Okay. Is there anything else I wanted to point out here? Yes. So looking at this equation, I created that variable where I had a smaller sample size. So I think the ones I was just showing you was like 10,000 observations. If I did the same thing, and I ran the same joint hypothesis test, but I did it for 1,000 observations, what's going to happen to my F statistic? So if n goes up, what's going to happen to my fraction in the denominator? It's going to go down. If my denominator is smaller, what's going to happen to my F statistic? It's going to go up, right? So, or hold on. So my sample size, because I'm explaining it as a sample size getting larger. If I go from 10,000 to 1,000, what's happening to my sample size? It's getting smaller. So if my sample size is smaller, my denominator here is smaller, so that fraction is going to be larger. So now I have a larger denominator. What's happening to my F statistic? It's now going to be smaller. So if my F statistic is smaller, what's happening to my p-value, probability of seeing that or anything more extreme? So the F statistic is moving this way. The area to the right of it is going to be getting larger. So I'll walk through this. So just to kind of be clear. So we had this F statistic was what? RSSR minus USSR divided by Q over, I think it's USSR divided by N minus K minus 1. Right? Let's make sure I got, yeah. So if I'm going from 10,000 to 1,000 observations, which I'll show you here in a second, this is getting smaller. So what's happening to this fraction? It must be getting larger. So what's happening to this fraction? It's getting smaller. So what an F statistic looks like is it has a long right tail. Kind of looks like a normal distribution with a long right tail. So if my F statistic was this before, here was my p-value. We said it's not a two-tailed test, just a one-tailed test, right-tailed test, because when I add in more variables, the R-squared has to go up. So if my F statistic is smaller, what's happening to my p-value? It must be going up, making it less likely I can reject the null. So we can prove this to ourselves with this data where we just ran this regression. All right, I've got an R-squared of 0.1085 when I included all 4 of those variables. Up here, I had created this small sample variable. So I'm now going to run this regression where I'm including, did I scroll down too far? No, I want this one, except for I forgot something, didn't I? I had exceptional and learning disabled here. Okay. So same regression, but now I'm going to run it just using that small sample. Okay. So if I do this, what should happen to the test? So before, remember, well, hold on. I'll do this. We'll go back up here so we can not to scroll as much. So here is the original regression with all 10,000 or about 10,000 observations. My F statistic was really large. P-value was basically 0. If I instead do this and only run this regression for this small sample, and I'm going to test those same two variables, right? What should happen to my F statistic? We just said it should go down, and my p-value should go up. Now, if I still have 1,000 observations, what could be true out to the fourth decimal? My p-value might still look like 0. But even if it does, so notice here, oh, why didn't it like that? Because I can't run that. Hold on. I got to show this. I'll show this to you this way. So maybe don't run this if you're following along, just because it'll kind of screw up your data. I don't want you to have to reload it. So I'm going to only keep this small sample. So what? Hold on. Small sample is equal to 1. What is that? Why is that not getting rid of everything? Oh, hold on. I know why. Because I didn't run this yet. This is why doing it in pieces. Sometimes I write this all at once. So now let's go to only keeping that small sample. Now, if I run this regression, there we go. So now, if I'm only using about 1,000 of those observations, what happened to my F statistic? Well, it's not 585, it's now 51, which is still very large. It still looks like my p-value is basically 0, but even out to the fourth decimal, I can compare those. What do I know has to happen to my p-value? Well, if my F statistic went from 500 to 50, even though it's still really close to 0, my p-value will be a little bit larger, right? So even if I give you examples where out to the fourth decimal, it doesn't look like there's a difference, you still know that there actually is. Right? Now, I probably won't do that on the exam. I'll give you something where you could like physically see that there's a difference between those p-values. Or I might just ask you, if you were to do the same thing with a smaller sample size, what would you expect to have happen to the p-value? You expect it to be larger. Okay? Sorry about that. I'll repost this. I forgot what I did. Originally, when I uploaded this data for you guys, it was more than 10,000. So I first created a small sample of only 10,000. I wanted to then change it to 1,000, but I already had a variable that was small sample. That's why it wasn't going down to 1,000. So you had to kind of recreate that small sample variable, and I forgot to do that earlier. So that is a lot for me to throw at you guys here today. So that should be the last kind of thing we want to talk about with joint hypothesis testing. This is going to be just another example. I'll probably save that for kind of next class or maybe even Tuesday, just so we kind of rehash it at a different point in time. Once again, that's all the new material. So what am I probably going to do? Well, probably. What am I going to do on Thursday? I've just got different data sets. We'll just kind of go through them and think about a lot of these different issues that we've talked about and just seeing more examples of them. So I try to kind of throw comments in the code so we can kind of go back and look and figure out exactly what topic it goes with. But we'll really just be going through more examples of all the linear regression stuff we've done from the very basic, simple linear regression. Now, if I'm studying for the exam, we spent some time on review because we're still reusing things like, is the p-value less than alpha, the idea of confidence intervals, all these things. But if I'm looking at the actual practice exam, notice there's only a few questions related to like sample means and doing hypothesis testing with sample means. The bulk of your studying should be spent on this linear regression, right? From the very basics, right? A simple linear regression, right? Just one variable on the right-hand side, all the way through kind of thinking about, here we had things like a dummy variable, right? In a simple linear regression. Here I've got multiple categorical variables where I've included multiple dummy variables, going up to multiple variables of every kind, right? And then thinking about all the issues that existed there, we've talked about linearity, variable bias, scaling the variables, significance, now joint significance. So really, I would spend the majority of your time thinking about all of this material we've talked about with linear regression. And this exam practice is supposed to give you a good idea about what the breakdown will look like on the exam itself. Okay, so this is like the holy grail going into next Thursday. I have a question for you guys, and I think I know the answer. And your answer is not necessarily going to change what I do, but I think that, I don't view myself this way, but to be in jest, I feel like I'm a fair and benevolent dictator, right? So I want to get a little feedback from what you guys would be kind of best for you. So I think I should have the time update on this. So as long as you get this submitted by, actually, I don't even care. I really care about the people who are here. So I'd appreciate if you get this signed. But what I actually want to do today, in case anyone's trying to game the system, don't help out your friends. On the way out, just sign your name on one of these sheets. That's going to be today's in-class quiz. It lets me know you were here. I also might run some regressions about who was here today and exam scores, just out of curiosity. So I'm going to kind of collect that, just sign in on your way out. But I would appreciate if you answer this also on your way out. So I think I have it set for points. I'm not going to have it factor into your grade. I think just based off how many people are here today, I want to do it this way instead. But I have these questions. So I generally am just interested. So it looks like there's 4 options. There's only 2. I was just lazy in creating this before class. I have the exam written. It's longer, right? So there's 2 schools of thought. You would have limited time in class, right? In which case, maybe scores would be a little bit lower, in which case I might be more likely to kind of use like a curve, right? However, right, I could also take a different approach, right? Because if you have more knowledge, you're still going to be able to do better in class. And then after the curve, I still should have rank ordered who knew the most, or who was most proficient versus those who weren't. I also like the idea. I also dislike it because I have to like really pay attention and see to make sure that people aren't cheating and really focus on the grade to make sure that you aren't, doing this with someone else. But I also toyed around with the idea of maybe taking a couple of the short answer portions of the exam and making it kind of a take home, right? So that way you would have probably more than adequate amount of time to answer just the in-class exam questions. And then before that next class, following Tuesday, you would kind of have to turn in, like I said, the exam will look like something similar to like 10, 11 multiple choice questions. Then I would probably give you 2 or 3 questions with various short answer, and then I would give you 2 or 3 take home, short answer kind of various points. So if I do this take home, what do you think I'm going to do with the grading? Be a lot more, harsh, and probably not end up giving a curve. Definitely not giving a curve. So that's kind of the trade-off, right? So I'm just kind of pure, like I said, this is not going to make my decision one way or the other, but I'm toying around. I just kind of wanted to I want to know your preferences. Would you rather have something where time is more of an issue and then there's a curve applied to it, or time is not an issue and you have a take-home portion, which is just graded a little bit more harshly, right? But you have more than adequate time. Okay? So if you don't mind responding to this before you leave, like I said, I just kind of want to get an idea about where you're at. Make sure you're signed that you were here during the way out before I let you get out of here.
So the partially take home, is there still going to be like a time limit for the longer one, like the quizzes, or is it just that one?
No. So this would just be something that you then hand in on following Tuesday's class. Yep. Yeah. Yeah, it would be the same questions that I would use in class versus, so like basically the in class stuff I have right now, I think it's 5 short answers with a couple different parts to them. I would just take like 2 of those and make that part a take home. Right. So just making it a little bit shorter in class and kind of putting the harder stuff probably for the take home and then grading that a little bit more close. Is that okay? All right. So Thursday, I just read, going through more examples, seeing the same material, just with different variables, different data sets. Other than that, if you have any questions on the way out, feel free to ask me. I'll see you guys on Thursday. Yeah, either way, the multiple choice questions will be in class. It's just the 5. The short answer would be, I would put about half of the short answer would be take home, half would be in class. Does that make sense? Yeah. Yeah. Huh? Oh. Thank you.